Alright, the last part of the chapter here is about radioactive decay. And we're going to start off with a little bit of background information behind how a few important people came up with the idea of radioactive decay, then what it is, and a few little aspects about it. So we're going to start off here with Antoine Henri Becquerel, and you usually do not see his name with the Antoine in front, and he is from around the late 1800s, okay? And what he was doing is he was studying the connection between light emission of these uranium compounds after they were exposed to sunlight. And what he did, or how he did this, was he took a photo plate and he placed a piece of uranium on top, or a uranium compound on top, and then he placed it in the sunlight. And the plate was supposed to be exposed because you want to look at this uranium, and when it's exposed to sunlight, how it will emit some kind of particles. Well, what happened was he saw that the first time, and then the next day he went out, and it was a cloudy day, so we didn't have any sunlight, and he put this uranium compound on top of another photographic plate, put it outside, and he wasn't expecting anything to happen. Well, what actually happened is that the photo plate still kind of got developed, and he saw these splotches there. So that was the first time that he thought he saw radiation. So this meant that sunlight wasn't needed for uranium to emit particles, or emit what we now call radiation. And he was the first one then to look at the idea of radioactive decay, where uranium spontaneously emits particles, or decays, okay? So he's kind of the beginning person here. And then you have Marie and Pierre Curie, and they were about right around the same time that he was. And unfortunately, Marie was a little bit later than Becquerel, and so she didn't quite get the immediate credit that he did. And what happened with her is that she was studying uranium and thorium compounds, and she was seeing the same thing that he was, with these spontaneous particles being emitted. And she was actually the one that coined the term radioactivity. And like I said earlier, she was in a race with Becquerel for discovering ideas dealing with radioactivity. And she actually discovered two other elements: polonium, which she named after Poland, her native country, and radium. Okay, and she actually later then died from radiation poisoning due to all of her work. But Marie and Pierre were actually husband and wife, and Pierre came in and then joined her research as well, looking into all of these different radioactive particles. So these two are the main people, and Pierre, that started off looking at radioactivity. So now we're going to talk about exactly what radioactivity is and radioactive decay. Okay, well, what it is, it's spontaneous emission of radiation. And spontaneous meaning that you don't need to do anything to get this to happen. It just happens. Okay, it's usually a decaying from a heavier nuclei to a lighter one. And this nuclei is then accompanied usually by an emission of radiation or emission of particles. And it took a while for people to figure out exactly why things radioactively decay, why this element turns into that element, or decays to a different one. So here we're talking about one element decaying into a different element, one nuclei changing to another nuclei. So we're talking about changing elements and emitting particles, and they want to know, why does this happen? Well, it happens because it will gain stability. So nuclei decay to gain stability. We're going from one element to a new element, and we call these nuclear reactions. I'm going from copper to zinc, or I'm going from iron to scandium, or going from polonium to uranium, or uranium to lead. Okay, changing what the actual element itself is. It's a little bit different than what we've been looking at with the chemical and physical changes. Okay, we call these radioactive nuclei which means these are unstable nuclei that undergo a decay. So if you talk about a radioactive nuclei, it's a lot of the bottom of the periodic table is radioactive, and those are then undergoing a decay to something that is a little more stable. And there are three main types of radiation that we're going to talk about that are emitted when these particles decay. And the three main types we're going to look at start off with an alpha particle or an alpha decay. Okay? Alpha particles are helium-4 nuclei that get emitted. Okay? When you look at radioactive decay and alpha particles, you'll sometimes see a symbol that looks like that. Okay? That's another symbol for an alpha particle. Alpha particles are very heavy, as we talked about in the gold foil experiment with Rutherford. Since they're really, really heavy, okay, they're also really slow, and you can actually stop a alpha particle by a piece of paper or with a piece of paper. Alpha particles will actually only travel a few centimeters in open air. So they can't go very far just out and around. You're not absorbing tons of alpha particles from far distance. The only problem you have with an alpha particle is if they are ingested or inhaled. So if they're not going to penetrate your skin. Alpha particles are not something that's going to seep in through and then you're going to have all kinds of radioactive poisoning. No, okay, they're too heavy for that. The next kind of radiation we're going to look at are the particles that get emitted, okay, as one element changes to another element, is a beta particle. And this is an electron, actually. And beta particles have a symbol that has like a bee with a little like a tail on the end. Okay, beta particles are lighter since they're electrons. Okay, so it takes a little bit more to stop these. These are actually stopped by lead. Okay, and they'll actually travel a few meters in open air. So we're actually talking about electrons here, and you need a little bit more dense material to actually stop these from penetrating your skin. So these are things that actually could be absorbed into your skin. Okay, the third type of radiation we're going to look at is gamma radiation. So these particles are particles that get emitted that are high energy. They actually have no mass, and they often will accompany another type of decay. Okay, these are very, very, like I said, high energy. They move very, very fast, and you actually have to try and stop these particles by layers of concrete and lead. And alpha particle symbols look kind of like a Y. So these are the three types of radiation that we're mainly going to look at. Okay, and these are the particles that get emitted when one nuclei decays into another nuclei. Okay. When we talk about radiation, okay, and different types of radioactive decay, we have what we call a half-life. And a half-life is the time it takes for half of the atoms of a radioactive nuclei to decay. Okay, and more stable nuclides have longer half-lives. It takes them longer to decay into something else. Okay, so we're talking about like uranium-234 decaying into thorium-230. All right, and if you look at this picture here with the uranium series, we're going to talk about decay series in a second. You see a little number by U-234, and that says 250,000 years. So it takes 250,000 years for uranium-234 to decay into thorium-230. Okay, half-lives again is how long it takes for half of it to decay. When we look at these decay series, like I was just mentioning, okay, so when we talk about decay series, okay, these are a series of nuclides, okay, produced by a successful decay until a stable nuclide is reached. And a couple of terms here, the heaviest nuclide are called parent nuclides, And the ones that are produced by decay are called daughter nuclides. And any element, okay, that has an atomic number greater than 83 is radioactive. And they are in one of three series. And you can see these three series over here on the picture. Okay. Notice how you start out in the top one with uranium-238. Then you're going to decay into protactinium-234, then uranium-234, then thorium-230, and it keeps going, keeps going, keeps going. To get all the way to the left of that one where it says lead-206. So that's one decay series. Then you see the other decay series before that starts with thorium-232. And then you see the other decay series below it, which is sometimes called uranium-235 decay series, but it also starts with Pu-239. So one decays into the other. And notice how all three of them decay into lead. Okay, lead is very, very stable. Okay, another part of radioactivity is what we call transmutations. And transmutations are things mutating, meaning that we're changing from one element to another element. And this is exactly what radioactive decay is. You're going from one type of element to a new type of element. Okay? This is something that happens naturally, but you can do this artificially. Okay? If you have artificial transmutation, that means that you're going to bombard nuclei with charged and uncharged particles. And when they were doing this, they were actually filling in the gaps of the periodic table. 43, okay, was produced synthetically. 43 is technetium. And then they also filled in the gap of number 61. And 61 is promethium. So these two were actually produced synthetically, which is why if you look at the big periodic table at the back of the room, in my classroom, those are outlined in like what? They're white, outlined in black. Okay, those means they were synthetically produced. And the last kind of term here is what we call transuranium elements. These are elements that have more than 92 protons, meaning it's uranium and the rest of the table. We call those transuranium elements. Okay, two other aspects of radioactive decay are fission and fusion. All right, we should have had these hopefully our freshman year. When we talk about fission, okay, fission is where a heavy nuclide splits into a lighter one. And the lighter ones, again, are more stable. Okay? When this happens, you release a lot of energy. And it can be spontaneous fission, or it can happen when it's bombarded by particles. And these are the ones when we're looking at nuclear energy. Okay, that's fission. Nuclear power plants, that's fission. Okay, and notice in the picture there, you see a 10N, which is a neutron. The neutron then hits a uranium-235, which then breaks apart that uranium into 141 barium and 92 krypton and 3 particles and a lot of energy. This is then when we get into, like I said, nuclear energy and chain reactions and things like that. That's all fission. Okay. Now fusion, on the other hand, okay, is where you have low mass nuclei that combine. And they combine to form heavier, more stable nuclei. Okay? Now the problem with fission is that fission also releases energy, but it releases more than fission. Okay? And fusion is what powers the sun and stars. The reason that we don't use fusion for actual, instead of like fission reactions for energy, is that fusion needs too high of a temperature to be feasible. There's no material that can actually contain a fusion reaction. That's why it's for sun and stars. Those are very, very, very high temperatures. And notice in the picture there, you have 2 nuclei. We have a deuterium and a tritium, which are hydrogen isotope names, okay, that combine fuse together, we get helium, a neutron, and lots of energy. So 2 low mass nuclei combining to make 1 heavy one. Okay, the last thing we're going to look at is radiation detectors and then a little bit about radiation exposure. Okay, so we're going to start off with the exposure part. And there are 2 ways that we're going to look at measuring radiation when you're exposed to. First one is called a Roentgen, and it's an R. Okay, it's a unit to measure nuclear radiation exposure. So if it's just one of many. There are others, Becquerels, there are Curies, okay, and I'm sure there are a couple more that I'm not saying right now, but this is one of the main ones. The other one that does a little bit more what we look at is what we call an REM, and this is the unit to measure the dose of any type of ionizing radiation, which means any kind of nuclear radiation, okay, that factors in the effect that radiation has on human tissue. Meaning it's measuring specifically how this radiation will impact your skin. And so for that reason, an REM is the Roentgen equivalent for man. So REM. Okay, and just as another side note here, long-term exposure to radiation can cause DNA mutations. And like I said, Marie Curie actually passed away because she worked with radioactive material too often. So then how do we detect this radioactive decay, this radiation that gets emitted? That's not always very good for us. Okay, we have what are called film badges, and you see a picture of them here. This is where the exposure of film is used to measure radiation levels. And this is usually for people that work with radiation. So it's people that work around X-ray machines or people that work specifically with a certain type of radiation. It will change colors usually when the radiation level gets too high. Another type of detector, and the last thing, is what we call a Geiger counter. And Geiger counters detect radiation by counting electric pulses carried by a gas ionized by radiation. So this radiation gets absorbed through usually a little handheld part in the Geiger counter, and it then ionizes some kind of reaction, and that reaction emits an electric pulse, and you hear like a little, kind of like a beep, okay? And you see a picture of a kind of old school Geiger counter here, and then also a new, more digital one.